Faraday's law in its most basic form isn't too terrible if all you're trying to calculate is magnitudes. But if, God forbid, you also need to figure out the direction of induced effects, things can get complicated. For example, if you're waggling a magnet near a coil and you want to know the direction of the induced current in addition to the magnitude, you can do that by looking very carefully at the directions of the magnetic field, the orientation of the loop, the rules for relating area and path integrals, and so on and so forth. But that's hard. Really hard. In a bit of luck, though, someone found a way to take all that math and express it in a couple of really general sentences, which we call Lenz's Law. Lenz's Law says that if you have a Faraday's Law situation, any induced effects will be oriented in such a way as to oppose the change that caused them. I like to think of this as basically being the minus sign in Faraday's Law, though there's a bit more to it than that. Let's look at some quick examples. Here's a loop of wire viewed from top down. Let's say there's also a magnetic field in the neighborhood, pointing into the page. And let's suppose we turn off that field over some time interval. As that field is shrinking, we have a flux through a loop that's changing. That means we'll be inducing an EMF in that loop and driving a current in that loop. But is the current clockwise or counterclockwise? Lenz's law says that induced effects oppose changes. Okay, well, the induced current, whatever it is going to make a magnetic field of its own. That magnetic field must therefore be opposing the change that leads to the induced current. The original magnetic field is into the page, but it's getting smaller over time, which is to say it's becoming less into the page and more out of the page. The direction of the change in B is out of the page. And so to oppose that, the induced current must be making a magnetic field into the page. And the right-hand rule tells us that such a field would come from a clockwise induced current. So that's the deal with Lenz's law. Rather than futz around with the directions of integrals and dot products and fields, we analyze the problem qualitatively in terms of changes and mechanisms by which we can oppose changes. I want to emphasize that Lenz's law is really general. You can look at any induced effect from any cause, as long as it's a Faraday's law situation, and figure out what's happening. Here's a crude magnetic braking scheme. We have a cart with solid metal wheels, and it's rolling forwards. And on the rails, we have some permanent magnets making some magnetic field. As the cart's wheels pass into the region with a B field, there'll be a changing flux through the wheels. And that changing flux will induce an EMF, which will drive a current through the wheels. And if you have currents in the wheels while they're in magnetic fields, you get magnetic forces on the currents. Now, to figure out the direction of those forces, you could go through real careful with Faraday's law and look at the direction of the B fields and the changes and the currents and do some cross products and yada yada yada. Or we could use Lenz's law. The force on the wheels is ultimately an induced effect, and it will be oriented in such a way as to oppose the change that made it. The change that made it is the motion of the cart to the right, from wheels rolling clockwise. Therefore, the induced forces on the wheels will be in such a way as to slow the wheels down, as shown. Much less painful that way, and a good example of just how general Lenz's law can be.